Look at a modern AI powering a robot. At its core, the algorithm is performing pure math, specifically next token prediction. Yet, this mathematical sequence successfully commands a physical robotic arm to execute precise movements in the real world. How do abstract numbers move cold steel? There is a massive physical gap here. Lines of code lack a sensory apparatus. They have no eyes and no ability to physically touch the objects they are manipulating. For decades, cognitive science relied on the symbol grounding problem to explain this gap. The assumption was that for a word or a token to possess true meaning, it eventually has to point back to a physical sensory experience, a qualia, like the actual sensation of heat or the optical perception of color. According to cognitive scientist Professor Ellen Barinholtz, this premise is incorrect. The simple grounding problem is a fallacy. Language requires zero physical grounding. It is a sealed, autonomous system that never actually references the physical world. If meaning is ungrounded from physical experience, the traditional rules of linguistics collapse. It suggests that our baseline assumptions about how human consciousness and artificial general intelligence operate are structurally backwards. To understand how a sealed system generates logic, look at how a large language model assigns meaning to a concept like red. It receives no optical input from a camera. It derives meaning purely through statistical co-occurrences with other text. Through a process called tokenization, words are converted into numeric vectors. The system does not recognize vocabulary. It processes lists of numbers. This 3D spatial coordinate system represents a linguistic embedding space. Here, those numeric vectors are plotted as nodes. The semantic meaning of a word like red is defined by its geometric proximity to related nodes like orange and color. As the model expands, we see the topological structure of the space. It is a network of relationships all the way down. This closed geometric web generates internal coherence on its own, without requiring any external physical data. The success of text-only models demonstrates that language contains all the necessary internal rules to self-generate complex reasoning. The system solves logic by mapping the spatial relationships between tokens. Because this geometry reliably produces high-level reasoning, human language likely operates on this exact same architecture. Our linguistic mastery is a self-contained computational loop, divorced from our lived sensory experiences. This topological approach redefines memory. We often assume the brain retrieves static facts from a storage drive, similar to retrieval-augmented generation, or RAG, in AI. But the human brain does not perform explicit database searches. As this diagram shows, what we call long-term memory is actually a set of static, fine-tuned matrix weights. Incoming data vectors pass through a matrix block of potentialities to produce new output vectors. There are no external database nodes, only mathematical potentialities waiting for input. Working memory is an active autoregressive sequence. The previous output vector loops directly back into the input stream alongside new data, creating a continuous processing cycle. This is the mechanism behind the tip-of-the-tongue phenomenon. You are not experiencing a failed search query in a mental database, but a short circuit in this autoregressive generation loop. Within this cycle, previous tokens in the sequence exert a decaying mathematical influence over the current generation. What you said 10 seconds ago guides the math of your next word, while what you said an hour ago exerts a weaker pull. By combining this continuous, decaying feedback loop with the fixed nature of those long-term matrix weights, we maintain context over the duration of a conversation. Viewing human cognition as an autoregressive matrix operation eliminates the need for separate storage and computational systems. If memory and processing are the same topological function, the technical requirements for AGI align with existing neural network architectures. This introduces a paradox. We have two isolated models. Linguistic space maps abstract textual tokens. Perceptual space maps entirely different variables, like light waves, geometry, and motion. Consider animal perception. A dog understands the physics of a door. It navigates the physical space perfectly without possessing any linguistic vector for the word door. The philosopher Wilfrid Sellars addressed this barrier in The Myth of the Given. He argued that raw, unconceptualized sensory data cannot simply be extracted from perception and directly dropped into a linguistic format. Mathematically, a direct one-to-one mapping between these spaces is impossible. The linguistic token for microphone does not contain the high-dimensional sensory variables, the specific shape, weight, or metallic reflection of a physical microphone. If direct translation is mathematically and philosophically invalid, how do these two alien spaces coordinate a real-world action like pick up the red ball? Solving this specific mapping paradox is the absolute prerequisite for progress. We cannot move from narrow, text-only language models to embodied general intelligence until we determine how these isolated spaces communicate. Recent breakthroughs regarding the universal geometry of embeddings offer a mechanism. Researchers have shown that completely separate neural networks naturally develop matching structural topologies. The core experiment analyzed one language model trained exclusively on an English corpus and a second model trained exclusively on Spanish. If you isolate the raw numeric vectors for cat in the English model and gato in the Spanish model, the arrays look entirely different. There is zero obvious correlation in the numeric strings. Then researchers projected the entire English cluster and the entire Spanish cluster into a new, higher-dimensional manifold. In this central 3D space, as the distinct point clouds push together, their structural shapes lock into perfect alignment. This manifold acts as a Platonic latent space, enabling translation via geometric relationships, bypassing any explicit dictionary. The models achieved this translation capability without ever being fed a single piece of paired English to Spanish training data. This mathematical phenomenon provides the mechanism needed to bridge any two alien computational topologies. If it aligns English and Spanish, it provides the framework to connect abstract language and physical perception. We can apply this exact experiment to the human brain, substituting linguistic space and perceptual space as our two isolated neural manifolds. When you see a microphone, visual input activates a geometric node in perceptual space, sending a projection into a shared latent space. Simultaneously, a spoken prompt projects from your linguistic space into that same central manifold, intersecting the perceptual projection before returning. Your linguistic model queries the latent space to extract the necessary structural potentiality. It uses that geometry to generate the correct output token, yes. The text model in your brain never actually sees the microphone. It handles zero raw visual data. It merely interacts with the shared geometric topology. This process works in reverse. Linguistic commands trigger structural changes in the latent space, which project down to guide the motor cortex to perform physical actions. The human mind is not a single unified processor. It is a network of autonomous geometric spaces communicating strictly through universal structural translations, thus preserving the autonomy of language. This reveals the flaw in current multimodal AI. Strong-arming visual pixels directly into text-friendly tokens is a fragile brute force trick that ignores the natural isolation of these systems. The AGI roadmap requires engineers to allow sensory and linguistic models to train and scale independently, linking them only via an untrained shared latent sandbox. These topological structures suggest LLMs are uncovering universal logic rather than simply mimicking a text corpus. Barinholtz expands this cognitive model to the nature of state-dependent systems. As shown in this fluid dynamic simulation, reality operates in a non-Markovian fashion. The universe's past states are computationally embedded directly in the present moment to determine the calculation of the next frame. There is a direct parallel between the auto-regressive memory of the cosmos tracking physical continuity and the context window of an LLM tracking a conversation. The interplay of these isolated auto-regressive spaces provides a candidate architecture for AGI and a mathematical framework for human consciousness and coordinated action.